Hello, my name is Gain Kim. In this lecture, I will be talking about a practical design methodology for continuous time linear equalizer, which is widely used in modern high-speed wireline transceivers for a wide range of applications. This slide shows where CTLE is used in different types of wireline transceivers. Typically at beyond 100 gigabit per second data rates, DAC, ADC, and the DSP-based SerDes architectures are quite widely adopted, where the TX-FFE performs partial equalization and the receiver side analog front end shapes the pulse response, and the rest of the heavy equalization is performed in the DSP on the RX side. And for analog mixed signal transceivers operating typically below 100 gigabit per second data rates, analog front-end equalization plays a more important role as an energy efficient equalizer. Despite these architectural differences, CTLE is commonly employed in both cases as a key equalization block in the receiver side on the front end. While the optimal CTLE response may differ depending on the overall system architecture and equalization strategy, its fundamental role remains the same, that is, to provide partial compensation of the channel loss in the frequency domain. So in this lecture, we will focus on how to design this CTLE in a practical and systematic way for high-speed wireline receivers. As shown in this figure here, the channel typically behaves like low-pass system, so higher frequency components experience more loss than low-frequency components. The CTLE compensates for this frequency selective loss by boosting high-frequency components, which effectively reduces the inter-symbol interference cursors in the pulse response if you look at the pulse response shown here in the time domain. As a result, the eyes become much more open after CTLE is applied. However, designing a CTLE in practice with optimized response is not always straightforward. Although simplified equation can describe the behavior of CTLE, they don't directly translate into circuit-level design parameters. As a result, CTLE design often relies on iterative optimization, and without sufficient intuition, identifying appropriate design parameters is not always straightforward. On top of that, the optimal response depends on the channel characteristics and overall system architecture, making the design space highly dependent on the practical constraints. So in this lecture, we will study a practical design methodology for CTLE. We will first learn how to define a target frequency response based on the channel characteristics, and then we will see how each circuit parameter affects the frequency response. And finally, we will look at how to choose those parameters in practice. Here is an example that shows the effect of CTLE on 56 gigabit per second PAM4 receiver. The channel shown here exhibits about 12.7 dB of loss at Nyquist, which make it difficult to maintain an open eye if you look at the eye diagram shown here. With the CTLE applied, the high frequency contents of the waveform are boosted, as shown in the highlighted box here, which reshapes the waveform and helps recover the signal. And as a result, the eyes become much more open after CTLE is applied. So in this lecture, we will go through a step-by-step design example for this kind of system. Thank you very much. I look forward to seeing you in May.